Please share your screen. And I should add that we will have the questions after the talk. So I would like Alfred to give his talk, and at the end we collect the questions, and maybe the president of SOTIAS can help.
Okay, very good. So I hope you can see the screen here. And to be honest, I didn't check whether my timing will be right, so whether I will end in time. But I'm sure Hans will give me then a hand and tell me how long I can talk. Yes. So, but I'm trying to keep it to 45 minutes from here on. Okay.
I'll give you a 5-minute warning.
Yeah, that's fine. That's fine. So without further ado, let me address 5 points here. What is SOFIA? Why does SOFIA need? Why does astronomy need SOFIA? What is FIFI-LS? Some SOFIA science highlights, and what can SOFIA do for you in case you're interested in working with SOFIA. And I would also give some credit to the deployment team here to Chile, because this is such a special place and also such a special team, and to give you some understanding what it means to send SOFIA here. So it's a mini deployment, so the team is smaller than it used to be, but the aircraft team led by Ed Harman consists of about 30 individuals. Then and I don't have the names because it was too complicated. The USAA and the DSI team together care for the telescope and FIFI-LS and do maintenance operations and science. And the USA consists of 23, and our German team as a junior partner consists of 9, and you see the names here. So if you count them all together, we are about more than 60 people, so about 65. And so 65 individuals came down here to Chile to run this deployment. And thanks to the team, we had a very successful deployment. I can say we got 7 out of 8 flights and no hiccups, except the first flight was cancelled due to a hardware failure in front of the telescope. Okay, SOFIA is a unique and one of its kind flying observatory, and you see a picture here. Maybe you visited the international airport, and you could see it standing there on the tarmac. Before I go into details, here are some basics about the project, so that you can that you know what this all is about. So it's as Hans already mentioned, it's an 80-20 USA-German project. It has a 20 years lifetime. So this is what it was built like. The home is in Palmdale in California. The aircraft is a B747SP. So SP means special performance, and that means it's a shorter version of the whole thing. So it's not a usual longer one, but the shorter one, it means the flying altitude is higher, and it can fly for a longer time. So the flight level therefore goes up to 45,000 feet, which we sometimes go for, but usually we end up at 43,000 feet, and this is above the normal level for aircrafts, which is at 37,000 feet or 38,000 feet. So we are flying pretty high above all the other aircrafts. First flight was in 2010, first science also in 2010, full operation since 2014, and we have yearly proposal cycles and deployments to Germany, other places in the US, to New Zealand, Tahiti, and this is the first time to Chile, which is a very nice opportunity. And we fly about 100 flights per year, and each flight has about 8 hours science time. So the flight itself is usually roughly 10 hours long, and but you have to climb, you have to go down, you have to prepare everything, and so we have 8 hours for science and flight. And the general science focus is fine-for spectroscopy in our galaxy and nearby galaxies, but we do a lot of different other things also. For example, it's occultation, because it's a mobile observatory, and we can go anywhere, anytime. And when there are opportunities, and I'll show you an example of that. Okay, so SOFIA is an aircraft that flies into the stratosphere, which is very high, and here you see a picture where this where a opening opens in the back of the aircraft, and this opening is a real opening. So there's no foil, no glass, nothing. So it's straightly exposed to the stratosphere. And if you have a closer look in there, you see that there's a complicated structure that we can that I want to share with you. This is the door has about the size of 4.5 meter, which is about twice the normal door sizes of a garage door. So it's a pretty huge opening here. And if you have a look inside, there's this telescope here, which is where you see the main mirror and down here. So this is the dark side of the telescope, because this is all carbon fiber structure. You know, here's this is a secondary and the holding structure here. And you see the two cameras here, the wide field camera and the fine field camera. And we have a third one, which looks directly to the telescope. And if you are going into the dark interior of the telescope, here you see this is the main mirror. It has a diameter of 2.7 meter. It's chopped down optically to 2.5 meter, because we do chopping, if you're familiar with this, and also to collect the waves in the fine infrared, you need a little bit more space on the mirror. So the telescope primary is a very short one in order to fit into the aircraft body, and the difference between the vertex and the circumference is about 14 centimeters. So it's really like a bowl thing. Once the light comes down and is reflected by the main mirror, it is then again reflected by the secondary here, and then by the tertiary, and sent into this tube here, and ends up on the bright side of the observatory, which is then here. This is the missions operations deck, and you see the telescope in the back here. And if we have a closer look there, so this is the other side of the tube, and at the flange here there sits FIFI-LS as an instrument, and picks up the radiation and analyzes this, and then the rest and the information then is sent via wiring and cables to the control computer and is stored there. So this is this looks like a complicated instrument, and I can tell you it's a complicated instrument. Everything has to work together: the aircraft, the telescope, and also FIFI-LS to get the result. Okay, in the fine infrared, you can address a couple of important astrophysics questions, and I name a few, and mainly those where we think that also SOFIA can contribute. And some of these are questions about what is the impact of massive black holes on the chemical and dynamical evolution of galaxies. So what's happening in the centers of these galaxies, and what can we see there? And also the flow of matter, so flow of gas, metal, and dust into, through, and out of the galaxies. So dynamics of interstellar matter and so on. And in what sense is the galactic energy budget universal? Recall that half of most galaxies, half of most galaxies' total energy is emitted in the far infrared. So they emit most of, or half of the energy in the infrared, and that has to come somewhere, and that has consequences. So how do star-forming structures arise from and interact with interstellar matter, and what regulates the structure and dynamics within molecular clouds? So these are questions that address more the evolution of galaxies and groups of galaxies. And then more on the smaller scale, we have the star formation and context. For example, how does multiplicity affect the way a star lives and dies, and how do massive stars form, and is planet formation fast or slow? We know that when massive stars form, there is not much time for planetary systems to form, and what determines the range of planetary system architectures. So in the process of the formation of planetary systems, so how does how varies the outcome if you vary the input parameters in the building procedure, and what determines the properties of individual planets in a planetary system. So for all of this, you can ask the far infrared and you get some answers, and some of these are also addressed by Sophia. Okay, let me see. Okay, there's more to that. The far infrared allows you to go beyond the surface, and you are certainly familiar with the infrared, and this is a small example here that you know, the Eagle Nebula, and with an image with the HST, which shows the surface of these dense clouds very clearly, and only if we move to the infrared, then we can look through these structures, look into them. We see stars that we haven't seen before, for example, this one here, or this one here, or this one here. We can look through, and you see even in the near infrared, this is not completely or entirely transparent, this column here, but if we go to the far infrared, then basically everything becomes transparent, and we can look inside these sites of very dense dust and gas and analyze its content and whatever is happening there. So the far infrared allows you to see the whole picture. That's the point here. And there's a third point why we go to the far infrared, and you can see it here. The far infrared is basically the range between 30 and 300 micrometer, but the atmosphere is opaque there. So this is a transmission, and the transmission is basically zero. Even from the highest mountain that you can have in Chile, and Chile has very high mountains, this does not change much. Of course, in near and mid-infrared windows open a little further, and this is used by telescopes here, and also you have ALMA on this side, but in the middle there, this is not possible from ground. Only if you go to the elevation where SOFIA flies, the curtain lifts a little bit, or mostly, and you can peek through, and depending on the precipitable water content, this curtain is higher or lower, but it opens to 80%. Okay, and this is exactly where SOFIA has its core science. And if you wonder what's to the left and what's to the right, I'll show you in a minute, but at the flight level of SOFIA, we have only 1,000th of the water content, which much improves the transmission. And we have much lower temperature of telescopic atmosphere, which means our sensitivity is higher. So both together provide a good basis for observation in this wavelength regime. On the left, we have JWST, which only recently became operational in the sense that they got the first sharp image of a star, so that's making progress. And on the other hand, we have ALMA, which is here located in Chile, and I think together these three instruments are complementary to each other. And I should also say that I think that technologically, SOFIA is I mean, the weak photon energy in this regime is really demanding technology-wise. But all of these instruments are great instruments. Okay, so let me see how to. Yeah, now then let's enter our next topic, asking the question, what is FIFI-LS? So FIFI-LS is the instrument that I just showed you that's mounted behind the SOFIA telescope, and FIFI-LS is a little complicated name. It stands for Far Infrared Field Imaging Line Spectrometer. And what it means is illustrated here with the antennae nebula. Excuse me. Antennae. First of all, it's a spectrometer. You get spectra out, but as you take the spectra, or when you take spectra, you are not getting one spectrum. You get 25 spectra. And to be honest, you get 50 spectra instantaneously. So you get 25 spectra from a 5 by 5 pixel field on the sky, here the red one, and you get 25 blue spectra, which is shown here. The pixels are shown here on the sky, and the red the red spectra belong to the red channel, which operates between 115 and 203 micron. And the blue channel, as we call it, operates between 51 and 120 micron. And they operate in parallel. So we have a dichoid mirror which splits the light. So the blue stuff goes to one side, the red stuff goes to the other side. We have two gratings, two optic sets, two sets of detectors, so that we can independently operate both channels. But the footprint on the sky is always related like this. So the blue footprint is smaller because due to the higher spatial resolution, due to the longer wavelengths, this is a factor of 2. So the blue spaxels, as we call them, spatial pixels, is each one is 6 times 6 arc seconds, and the red spaxel, the red one here, is 12 by 12, and each spectrum is immediately 16 spaxels, which are spectral pixels. Yeah, so this long, and so this spectrum that you get is 16 pixels long. So all in all, if you count it together, we have about 2 data cubes and each 400 pixels, so we get 800 pixels altogether, and the spectral resolution varies between 500 and 2000. The instrument itself is rather complicated, and I can give you provide a glimpse here. You see, if all the baffles have been removed and the instrument is warm, you can have a look inside, which we sometimes have to do. And you see a division line here. On the left side is a red channel. You see the mirrors are bigger. On the right side is a blue channel. The mirrors are smaller. You see the detector blocks here. They operate at 1.6 Kelvin, so this is pretty close to the absolute zero. You see that each detector block consists of 5 individual blocks, and each block consists of 5 columns of detectors. So here is your 5 times 5 spatial pixel, and then in the vertical axis you have your 16 spectral pixels. So this is 400 pixel and this is 400 pixel. And these are the 2 gratings, the red grating and the blue grating. And of course, a lot of wiring and signal lines. Okay, FIFI-LS is not alone, and we have more instruments available. Let me show you Hawk Plus. This is a far infrared camera and polarimeter between 50 and 240 micron. And Forecast is a mid-infrared camera and has also Grism, so that these two are complementary. And then we have the mid-infrared spectrometer is a shell axis, and of course, then beside FIFI-LS we have GREAT, which is a heterodyne spectrometer, very high resolution, and runs between 60 and 600 micron. And of course, we have a visible camera, focal plane imager, which is permanently mounted, and if it's not used for occultation work, then it's used as a guiding camera. And let me put some emphasis on mentioning that polarimetry in this broadness has only become possible with SOFIA. So now that we have a Hawk polarimeter available, we can do polarimetry in the far infrared, which is an excellent diagnostic tool and just developing. Okay, let me take you on a little tour here during a flight. So I thought this would be a little appropriate so that you get an impression. These are all pictures that either I took or some from the team. So this is Sophia standing on the airport of Santiago. And in the afternoon, there will be checks and cryofills and everything. And then this is a view inside Sophia when we do in the afternoon the functional checkout. So everybody is from the day crew is looking if the telescope is working well, if the instrument is working well, and making sure that the aircraft is working well. We had to exchange a tire because there was a metal piece punched into the tire. So these are things that we go for in the afternoon and make sure that the FIA is ready to fly for the next night. Then, of course, in discussions, we tweak the observing strategy because every time there is something different. the weather may change, the wind may change, so we may have to vary the flight plan a little bit, but this is how it goes. So this is daily business, and then when the sun starts to set, SOFIA is hopefully ready to go. But before we go, there will be a briefing, a mission briefing. So where everybody that's joining the flight will be sitting together and exchange all the information that everybody needs. We get weather updates. We get information on fuel, on special features that have to be accounted for and things like that. So here we're sitting together, and then after that, everybody rushes for the aircraft because we have to leave on time. Then we'll take off on time, on the minute. And why this is, I explain to you in a minute. So when we are airborne, we need to fly certain flight plans. And here you see all the flight plans that we have flown during this deployment. So this is the coast of Chile here, as you easily can see. Here is the southern part of Chile, and here roughly we have Santiago, and from here you see in different colors all the flights that we took. And you might wonder why this is such a chaotic pattern, and the reason is that recall that we are looking with the telescope out to the port side. So whenever we want to observe something, we have to steer the aircraft so that we are flying 90-degree angle with respect to the target. And okay, the target stays in the air, but the Earth is rotating under the aircraft, and this is why we get all these nice curves. So the telescope is inertially stabilized. This is one thing, and you can change, of course, the direction and then look for different targets. But at the end, when we are running low in fuel, you want to have a runway in front of you. So it's the task of the flight planners to put a sequence in place that allows you to look for one target after the other, and at the end of all targets, you are back in Santiago. And this is what we call efficient flight planning without any dead legs, and this is what comes out, what you see here. So one flight was last Saturday, and pretty far south, almost to the Antarctica. Okay, once we are airborne, then the telescope is being set up. Then next comes the instrument, is launched, and you see some head scratching here. So sometimes there's little hiccups, you have to restart things, but generally everything worked well. And if that is the case, then as we see happy faces as the data start rolling in. And this is console where FIFI-LS is being controlled. We have a team of about 6-7 people that deals with FIFI-LS, and you see other people around here. So the mission director, the flight planner, here on the left, telescope operator, and here is Dario. He belongs to the FIFI-LS team and is responsible for the data reduction, for example. So then then starts a quiet phase where everybody looks at the screens, and we go for the observation. And if everything, as long as everything works well and we have no crashes, then we are simply collecting data. Okay, this is a little, not an animation, it's a 15 times time-lapse photo that shows you how the telescope generally moves. I hope you can see it, at least maybe the picture jumps a little bit, but it goes up and down, and you see that this is a ball bearing. Oops, this is a ball bearing, and it can move in different direction, and it also has the ability to stabilize the telescope in case of turbulences. And here you see a movie that was taken a couple of years ago under heavy turbulences, where you see that the telescope moves with respect to the aircraft. So the poor guy sitting there with seatbelts on and is being shaken around. I can reassure you that the picture on the screen was rock stable, so we observed during that time, and this is kind of the inertial stabilization. So what you see as a telescope movement is really a movement of the aircraft, and this is what happens during the flight, that you see the telescope moving around, but the image is still very stable. And this is, of course, engineering-wise, this is one of the highlights of the whole thing, that we are able to stabilize the stars on the screen and for the instrument to a level of about 0.4 arcseconds RMS. So this is one example of how observing SOFIA is different. And let me briefly go through the list and read it to you, and you will understand why this is the case. First of all, you need to prepare a detailed and accurate flight plan. Then you have to obtain a training on how to evacuate the observatory. Take off on the minute, I explained that. The higher acceleration forces than on civil aircrafts, about, I would say, a factor of 2, yeah, to be honest. Inertial telescope stabilization, no deviation from the flight plan because you want to go home. Finally, change the altitude of the observatory. That's possible. This is a nice thing about SOFIA. And the flight level is inversely proportional to the precipitated water level. This is why you want to go higher if possible. Airspace control sometimes restrict your flight level. They say, no, you can't do this. There are some other airplanes in the way. Closed airspaces may pop up unexpectedly. This is like a virtual ball because you're entering military territory that suddenly becomes hot, and you have to, then the flight planner has to hectically replan. Control deck temperature is not always selectable, so sometimes it's warm, sometimes you are freezing. I don't know why. And there are two important things. You can't step outside and look at the sky, and there's no pizza delivery on site. So bring your own stuff. Okay, so now then let's turn to the science while we're observing. And I would like to share with you a couple of highlights that we have seen during the last years, and which you may not have been aware about. And I start with things that are close by. So I start with our local environment. Here, example is the moon. And there has been measurements on the moon with the forecast instrument, the GRISM spectrometer there. And they have observed the crater Clavius, which is on the southern side of the moon. Here you can see it on the left. And what Casey Honeybell found is that spectral indications of water enclosed in crystals, in crystalline structures on the sunny side of the moon. And this is the animation here, or the picture shows that. So you have water here, water molecules within closed crystal structures, and there is a spectral line here at 6 micron, which can only be seen from, because it's out of the absorption, which can be seen with SOFIA. And here is the region that they scanned. So now with this discovery, of course, there are plans to map a bigger part of the moon. So this is in progress. I can't tell you what has come out, but you will certainly hear about this in the next year or so. Okay, the next example is also within our planetary system. And I told you that SOFIA is a mobile observatory, and we can go where the action is. And in this case, the action is a occultation of Pluto with respect to a star. So Pluto casts a shadow with a star on the Earth. So Pluto runs at 4 kilometers per second. We are at 29. So roughly the relative velocity is 24 kilometers per second. And you can predict where the Pluto shadow on the Earth will pass. And that's usually not where the great ground-based observatories are. So we fly where it is, and sometimes, most often, over the ocean. So the shadow itself is about 2,800 kilometers wide. So this is due to that the Pluto has this diameter, and here is a light curve. And I want to briefly discuss this light curve because it looks very special. So at this level here, you see the light of Pluto and the star, and then Pluto moves in front of the star, and at this level you only see Pluto because the star is behind Pluto, and then here Pluto moves away, and then you see both again. So what does this mean here? This funny light curve. First of all, it means that if you put the size of Pluto in context, you see that the shadow is not like a shadow would be of a solid sphere, because then you would expect a light curve that looks more like this rectangular curve. So what this shows you that we are seeing an atmosphere here of Pluto on both sides, and the atmosphere, if you look at it, the slopes are different in different parts. This is steep slopes and a little shallow, and then steep again. And I have indicated this here with these layers. So we see layers of the Plutonian atmosphere here, and there is some more to that. And for example, this is noisy that you see. The noise is very low, but here you see all kinds of movements here, up and down, and this is not noise, this is real. And what it is these are cloud structures. So we see in the lower part of the atmosphere, we can observe cloud structures on Pluto, and depending how high you go, so you see that the clouds are mostly in the lower part of the atmosphere. Of course, then we have the central flash here, and this is, I think, known to most of you what this is. But before we come there, let me compare our finding of a layered atmosphere with some clouds to the New Horizon picture that this mission took at about the same time. And you see here the layered atmosphere of Pluto. So this is a very nice finding that fits together. Yeah, the central flash is the effect of caustic. So if the star is behind the Pluto, then the atmosphere here is bending the rays around so to the middle, and you see them in the center. So the fact that we see a flash is also indicative of the presence of an atmosphere. Yeah. So, okay. So what it means, all in all, is we can derive atmospheric temperature profiles. We can derive atmospheric pressure profiles. We can study cloud layers, and basically what it means, we get the weather status on Pluto simply by observing such orbitations. And this has been very important because we want to see how the atmosphere of Pluto changes as Pluto moves away from the sun on its elliptical orbit. And so if we revisit Pluto in a couple of years, maybe we see changes either in these layers or in these clouds or whatever, or in the extent of the atmosphere. Okay, the next example is a little further away within our galaxy. It's NGC 7027, which is a well-known planetary nebula. And the finding here was the discovery of helium hydride. Helium hydride, as you can see here, is helium plus a proton, basically. And this has, people have been looking for it because it is the first molecule that's going to form after the Big Bang, let me say. When the temperature is low enough that molecules can form, then helium hydride is the first one to form. So, but it has never been observed. Of course, here in the planetary nebula, it's not. I mean, it's being created by a different process than in the early days of the universe. But still, the discovery marks really our understanding of how these things can form. Yeah. So it's also the starting point of cosmic chemistry because it's the first molecule, and it's also important for the for the building of H2 here, because out of this molecule you can form H2. H2 usually cannot form directly in an atom-atom interaction, as you may know, but it has to have a third partner. Usually in our local universe, it's dust grains that where the atoms of hydrogen hop around and then transfer their excess energy to the dust grain. But in free space, that is not possible. And so there was a question how the first stars could have formed. Okay, so now this is starting point in chemistry. We have the first necessary step towards solving the mystery of the first generation of stars. So there's more to understand, but this is an important first step here. Okay, these were great observations. You see that we move through different instruments here. And our next example is, let me see, how do I get there? Yeah, it's the role of magnetic fields for star formation. And there we move to Hawk Plus, the polarimetric images. This is an HST image that you probably know very well, M51. There's the companion, there's the main galaxy, you see the red dots. These are sites of star formation, at least you see the hydrogen emission here. And last year we got the first image of the polarimetric map of Hawk Plus, showing the magnetic field lines in this galaxy to its full extent. And this is very impressive, because this is now for the first time that we can really study magnetic field lines and their role in the galactic and extragalactic content. And what it turns out, I mean, I'm not an expert on this, but it turns out that the magnetic field lines are well aligned in the inner part of the galaxy here with the and then we have some regions where they are distorted. For example, it's here, so where they are directed in several directions on small scales, and then we still have again have regions where they are well aligned in thinner and low density inner arm regions here. These magnetic fields are important not only for star formation, but they seem to trace the flow of interstellar matter. We have seen now a couple of images where they indicate also where the flow goes. And also for understanding the regulation of star formation. So with the study of this, we hope that we get a handle on a better handle on how the magnetic field lines interact with star formation processes. I should say that the polarization of it's a polarization of dust emission in the far infrared due to the fact that the dust grains are aligned in the magnetic field that provides a polarization and then and the means to reduce or to deduce the magnetic field direction from that dust emission. And since we can measure dust in emission, and the far infrared emission is a very good, the far infrared is a very good wavelengths regime to measure the magnetic field. There's more to that, because with FIFI-LS we have also done observation of the C plus 157 micron line, and this line is important in the far infrared because by itself it carries up to several percent of the volumetric luminosity of the galaxy alone, so 2%, 3% sometimes. So it's the main coolant of the diffuse neutral interstellar gas, and it's also the brightest, often the brightest far infrared emission line. And as a forbidden line, you know, this is an important cooling process for the galaxy, and it also reacts directly on input of energy input from massive stars. So whenever you see here a bright emission, that tells you that probably we have massive star formation. And the good thing is, since it's at 157 micron, it can still be observed at high Z galaxies, because then the emission is in the radio. but you can't see the spatial resolution there. So we study the details here and then transfer our knowledge to the high-Z galaxies and see what they do there and how they operate and what star formation looks like there. So this is what Hans once named the local truth. So locally we find out what's going on, and then we look at far distant galaxies to relate them accordingly. Okay, then I would like to share with you a result from this deployment. This is the M83, if I get this correctly. And this is almost face-on starburst galaxy. And we have so far, if you overlay a Herschel-Pax image, you see the dust. And if I toggle here, yeah, you can see that the dust emits where you see the dark stripes here. So the dark dust lanes here then start emitting infrared radiation at 160 micron. And if we now overlay here the first results of the 157 micron line, you see that where I told you that this is related to starburst and star formation events, you see that this emission very nicely follow the dust emission here. So the warm dust that emits radiation, reprocessed radiation from these star formation processes. And of course, this is the center here. So meanwhile, our map has grown a little bit. So maybe next time I can show you a more complete map. And there's also a official proposal on the table that wants to map the whole galaxy. Finally, or almost finally, let me come to the Magellanic Cloud, because the Magellanic Cloud brought us here, and I'm happy to be able to show you the first results. So this is a legacy project, and it was awarded 50 hours of observing time, but not in one go. But they told us, okay, first show us that you can do it. So we got 20 hours, and the role or the task was to determine the role of metallicity and the physical conditions of the molecular, atomic, and ionized ISM there. As you know, that the metallicity is a factor of 2 lower than our Milky Way. And so the plan was to observe the 157, I should read 157 micron, and the 0388 micron line, which we can do in parallel, as I showed you, towards the southern molecular ridge. Here, and then one of the main ideas was that these far infrared lines trace the molecular gas not traced by the zero emission, because we see molecular gas that is not related to the observable CO, because the CO may be destroyed already and by the radiation fields, but the H2 may still be there. So the idea was that in this regime here, and in this region here, we do a first check, and it turns out that the whole project was planned for this size. We got now I'm happy to report the first this field here. And from this field, I can show you a part in the first quick and dirty reduction, because this is a lot of work and our computers are too small to do it at the full resolution. So this is at the coarse resolution and the background is not really flat. This will come then when we are at home and the real reduction starts. This is already a field of 15 times 19 minutes, and we plan for 30 times 45 minutes. So I think this so far has been very successful, and I can say that we, except for this last 10% here, which was missed during the canceled first flight, everything else worked out perfectly well. And let me also mention that Monica Rubio and Hans Sinniger are part of the team, so they are co-eyes on this project, and I'm sure that Hans will have maybe some questions later about this. Okay, So do I have a couple of minutes left, or how are we doing? Yeah, I can't hear you because you're muted, but
3 minutes, Alfred.
okay,
You're just,
well, I'll make it quick.
you're just on time now, but we would like to have some time for questions.
Yeah. Okay, good. The galactic center is very well visible here from Chile, as everybody knows, and this is a picture from Paranal with a laser-guided star. If you look in the near-infrared, you see where the center really is, and there is a mid-infrared picture showing the hot dust from Lau et al. 2013, obtained with SOFIA, where we see the dust ring here, circummolecular disk, circumnuclear disk, and where the center, the black hole, sits here in the middle. And the interesting question is now, what is the connection of this central nuclear disk here, which you see here, to the rest of the central molecular zone. And so this is what you see there. And this is a ring here that indicates the size of the structure. And what we did is we observed the galactic center then with FIFI-LS and try to address some questions. Say, how has this structure formed? How stable is it over time? Do any stars form in it? How does it evolve? What is physical connection to the central black hole, and what is the physical connection to the galactic central molecular zone? And so we did some observations in C+ and other lines. I can't show you all the results. Some of them have been published here, but in C+, you see the same ring-like structure, and we also see velocity structure showing that the ring is actually rotating, and the velocity structure is extended here. So you can see this is blue shifted, this is red shifted here. The velocity is between 60 and minus 60 kilometers per second, very typical for the size and the mass of the black hole. So what comes out of all this is that the CND is a rotating structure of individual clouds streaming in from several directions. So this direction, but also from other directions. So it's a semi-chaotic process where everything seems to form then in place. And the velocity structure is dominated by the central black hole, and it's very probably dynamically connected to the central molecular zone via these via streamers here that you can't really see on this image, but on other images you can see them more clearly. Okay, so I'm mentioning this because this is also a target that's visible in the southern hemisphere. So now, as we come closer to the end of our talk and the night, then you see here, this is a picture from the other day. There's in the top here, there is Venus, and you see Saturn, and this is Jupiter just rising. Maybe you see it on your screen. And then our pilot is, as we are cruising through the stratosphere, is directing us towards the morning sun and approaching Santiago again. And here you see the Saturn. Here you see Jupiter again through the cockpit window as we start our descent toward, and the chain of the Andes here you can see. And so then suddenly there is Santiago in the dim morning light, where the first rays of the sun peak behind the horizon. And then there's a runway in front of us, and there will be a happy landing then with tired astronomers, and the airport of Santiago is greeting us as we enter the bus and fall asleep. So before we fall asleep, let me answer a question: what can SOFIA do for you? So if you're interested in interstellar matter, spectroscopy, far infrared dynamics, transits, evolution, excitation, star formation, normal, irregular, and interacting galaxies, then go to this website and maybe you'll find something useful. Write a proposal, and international proposals are welcome. So maybe, and if you have a successful proposal, then you are very much invited also for a flight in SOFIA. And with this, I thank you very much, and I'm ready for questions.
Wow. Thank you, Alfred, for this very nice overview of SOFIA, the plane, the instruments, the science, and I think particularly you managed to get across a vivid impression what it's like to observe and how it feels to be on the plane. It will not replace your personal experience, but he did a very good job to give you a sense of what it's like. Thank you so much. And the talk is now open for questions. I don't know who will collect the questions, or you can use the chat, but you can also raise your hand, I guess, to ask questions directly. I don't see the questions right now, but I can check the chat.
Exactly. You can raise your hand using the Zoom tool for that, or you can also post your questions in the Q&A section. So you may use any of those alternatives. We have one hand up from one of our panelists.
Yeah, sorry. Yeah, I'm first, sorry. Thanks for the talk and for letting us know more about this peculiar observatory that we're lucky to have you in Chile. And I would like to ask you about how was your experience here in Chile, your feelings. Maybe it's too soon to ask you, but if you have any future prospects about coming back to Chile and so.
Yeah, first of all, the experience in Chile was very good. I mean, everybody was very friendly on the airport. We had very good support from all people. So for the team, I think it was a very positive experience. And if we can, we will certainly try to come back. As you have seen, so far we have, there was only one flight which crossed the Argentinian border. Because this is an official state aircraft of the USA, there's always some politics involved. And so the pilots say, okay, let's try for one flight to get across the Argentinian border and see what our experience is. And the experience so far was very good. The point is, if we can move freely about, then we can set up more efficient flight plans. So maybe this is encouraging for the pilots, and next time we'll try something more, let's say, even more chaotic, going back and forth. And because for the galactic center and the Magellanic Cloud, it's better if you can move across. This way, we had to fly out over the Pacific, and the flight started very late at night at 10 o'clock. So if we can use the Argentinian airspace, then we can also start at 6 in the evening and find some sleep in the early morning, let me say. So we are kind of exploring the options here, and but our experience with Santiago Airport and the community is very good so far. So thank you. Yeah. Now I thank you very much to everybody. We found a lot of support, and I'm certainly very happy to come back here.
Okay. Other questions?
So I don't see any other questions on the Q&A. Oh, here we go. We have one. So from Mario Flores, he has a question. He says, could you tell us something about idea of complex molecular in space?
Idea of complex molecule in space.
Complex molecules, I think he meant.
Complex molecules. I mean, I'm not, maybe this is a question for Hans, but I can start at least answering it. First of all, we are trying to find the simple molecules, so hydrides and these things, because these are easy to identify in the lab. We have to identify them spectroscopically, and if you want to find them in the far infrared, we first have to know where the spectral lines are. So for simple molecules like water, you have a whole range of molecules very well known. And for other, we have also species, we have also lab measurements. But if it comes to complex molecules, we sometimes don't even know what their spectral signature is. And in fact, if you look, for example, to Orion, you see lots of spectral lines that have never been identified. So we are dependent on lab measurements from people who tell us which lines belong to which molecules. So only then can we observe them and identify them. And we have, for example, there was a proposal to observe lithium-7, and so there is a far infrared line for lithium-7, and we looked it up. So there is a Japanese lab now, Japanese lab measurements for lithium-7. So somebody has measured it and found arguments that it might be observable in the far infrared. So complex molecules can be observed, but you need to tell us which spectral line, then we can do it.
But can I add something? I mean, the thing is about the far infrared. I mean, the far infrared mostly traces rotational transitions, like this helium H plus is a rotational transition, and so molecules like OH or actually the deuterated species OD or H2D or HD. Those are the molecules that SOFIA excels. And then there are some with this other instrument. This is the far infrared, but then there is this mid-infrared spectrometer called EXIS, which actually measures low vibrational transitions of somewhat more complex, even organic molecules. I mean, so there is the far infrared is good for light molecules because of their what's it called, the moment of inertia. And so on. So complex organic molecules that are formed on dust grains, that's more, I guess, the realm of ALMA. They are heavier, and so, therefore the transitions are in the submillimeter and so on.
Mm-hmm.
I have a question too, if I can ask one quick question, Alfred.
Sure.
I was interested about the flight path and the flight duration. So when did you actually take off typically, and when did you land? And
we took off typically at 10 o'clock, 10:05, 10:04, and see, the flight plan is fixed. Now the Earth is rotating, so if you are not, so the aircraft moves with the Earth, so you have to take off on the minute, otherwise you will miss the flight plan. And this is why we stand at the runway, basically counting down the clock, and then then we get a lot of acceleration and we take off. And then it's always up to we have to be there at the right time, at the right spot, otherwise it doesn't work out.
Yes.
And I should say, since Julio mentioned this, so usually they reserve one of the two runways for us during the time that we take off, so that we can take off on the minute. So all the other airplanes go to the other runway and we take this, and then after we have taken off, then everybody else can come back and also use that runway. Mm-hmm. That was very nice.
Mm-hmm. We have a couple more questions in the Q&A, and one is from Rafael Rios. The question is, can we also forecast from the data via SOFIA what is the rate of formation of H2 from the observed helium H plus, as you showed in one of your slides?
Yeah, this is an interesting question, though. Thanks for the question. So first of all, the fact that we now can observe helium H plus confirms that this molecule exists. It doesn't show anything about the mechanism how H2 is formed out of helium H plus. And you can imagine that also the formation, as I mentioned, of helium H plus in the planetary nebula is probably different from the mechanism that helium H plus has formed in the early times of the universe. But there is a reaction chain that I can't show right now because I don't have the slides, how H2 can eventually form out of helium H plus. But how long this takes, I don't know. Usually this takes a long time. I mean, and depending on, of course, the condition and the density and the radiation field and everything. So where we know very little about. So it may take longer time or a short time. I don't know whether Hans knows more about this, but this remains to be modeled right now because once the molecule has been formed, we can take the next step. And this is, I think, you're pointing in the right direction. This is where we now have to think about.
Yeah.
Thank you. And we have one more question in the Q&A. It says, how does JWST affect the work of SOFIA?
Mm-hmm.
Yeah, this is a good question. I mean, right now, we are also observing between 5 micron and 30 micron because there is no other instrument that can do it. But with the, if JWST comes in operation, then we concentrate more on the core of our wavelengths regime. Also, JWST cannot do everything, but whatever it can do, it does exceedingly well and with a much higher sensitivity compared to SOFIA. So JWST will move SOFIA in a way that SOFIA will be more focused on its core business. So the, for example, the ground's rotational, the transition of H2 is at 28 micron. This is just beyond the capabilities of the JWST. So HWST cannot easily observe this this molecule, and this is an important transition. So this is where we can step in and say, okay, we can do it, and we can build instruments, and people have thought about building instruments observing this specific transition because it's important for the H2. So wherever the JWST steps in, we will not continue, but we have enough real estate to build instruments and proceed with observations in other fields. Also, you have to understand that as JWST works at shorter wavelengths with the 6-meter telescope, their spatial resolution that they get, the angular resolution, is probably or generally higher compared to SOFIA, so by a factor of 10 or so. So this is, let's say, if SOFIA has a disadvantage, is that its size is limited. We can't increase the size of a fine-field instrument easily. If you go into space, I mean, Herschel already was in the 3-meter range, and you have to go on a balloon to increase the size. Otherwise, it's not possible. And from ground, we can't do it either. So we are kind of a little bit stuck with the size, but we are in a regime where nobody else can observe.
And JWST is geared to very faint sources, so they can't observe. They're saturated for the bright source. They have to be careful. And so coming back to the local truth, some of the things are actually near our doorstep, and we can study them with SOFIA, which is then observed by JWST in the distant universe. That's one thing. But I wanted to make, if I may, one final comment, because this might be important for the audience, because SOFIA has been under threat or is fighting for survival, because the decadal survey, the recent decadal survey of the National Science Foundation has actually suggested that because you have JWST and ALMA, maybe SOFIA is no longer necessary. That is this is plainly wrong. And because, as Alfred pointed out correctly, SOFIA is actually complementary to both JWST and ALMA, and particularly the connection with ALMA could be even more explored. And the problem is that SOFIA is expensive. You saw how many people have to operate it, but it's like, I compare it with a doctor. If you need a surgery and it can only be done in a certain way and it is expensive, you will still do it. I mean, even if there is not 100 papers coming from it, on only 10. So really, this is an important consideration. And I think perhaps the support of the Chilean community, and if this deployment has been a success, maybe we can change the minds of people at NASA, because NASA is under pressure from whatever the decadal review says. So much for that.
Thank you. And there are no more questions in the Q&A, but I would like to ask something. Perhaps it would be nice if you could comment on the process of maybe people from the audience would like to have a proposal for SOFIA or something. So perhaps you could comment on the process. Perhaps you have certain times of the year that you are open to proposals or something like that.
Yeah, I can certainly comment on the proposal process. So as I said, once a year there is a call for proposal, and this is not issued at a certain month. I mean, we have tried this in the past, but we are currently moving a little bit through the year. And so you have to stay tuned in order not to miss the call. You will have to write something up in English and submit it. And there will be a time allocation committee meeting evaluating all of this. This will is taking place in the US. There's also a German time allocation committee, but you then have to have a Germany affiliated PI. So COAs can come from anywhere, including Chile. So if you know somebody in Germany and who is willing to be the PI on your proposal, then you have a second chance, so to speak. Yeah. After the evaluation of the two tags, then the successful proposals are put in a big pool, and then we go for trying to convert them into flight plans. So not every there are targets that are easily to observe, and there are targets which are more difficult to observe because the way the aircraft works and the flight plan has to match with boundary condition like fuel. And for example, the galactic center Magellanic Cloud is a perfect match. You know, you can on one way you observe one target, on the way back you observe the other. One of my PhD students works on NGC 253, which is also a southern source, which is not so easy to observe because you have to find matching targets for the way back. And so still we are successful with this, but so if you you have a higher chance that your proposal is scheduled, even if it's not getting the highest grade, if it's in a good place in the sky. And in order to find out, I can't give you this, but there are some experts who can eventually point. If you have a choice of 4 or 5 targets, then if you choose the right one, then maybe you get it easier than you get the other 4.
Correct. Very true. Wow, you covered a lot of ground, Alfred. Congratulations. Thank you also for staying awake for this talk, and even
I have my copy here, so to stay.
Yeah, and even dropping the Minister of Science who invited you to talk to him. So this is very, very noble of you. So thank you again. Any more questions? Maria Fernanda, would you close the session or?
Sure, I can close the session. I want to thank you both again. I want to thank Alfred and Hans for joining us, and I want to thank everybody who attended this talk. So we,
And
I
thank
don't
you
see
to
any more questions.
you. Thanks to you, because you
Thank you.
did the lion's share of work.
Thank you. So thank you, everyone. And we will close it up here and stop the transmission. Thank you, everyone who followed this. And you can also go back to this talk. It will be on our YouTube channel. So you're welcome to do that and share it with more people. Thank you again, Alfred. Thank you, Hans.
Yeah, thank you.
Good day, everybody.